Okay, yeah, so attention, we all know, we all love it. I am going to be going over a lot of different forms of attention. Um, Basically, if a form of attention exists, it will probably be covered in this, as in, like, this is going to be covering the general ideas of it. So, for example, the DeepSeek paper released some form of attention, and that attention is derived based off softmax attention, or the Titans paper. That is a form of this gradient-based RNN linear attention, which is a form of linear attention. So yeah, I'm going to basically be covering a ton of attention stuff, starting from the beginning. What is attention? So if you know what attention is, cool. Um, I will hopefully have other things that are useful. For example, if you don't know how masking the attention works, I will be going over self-attention, which is just normal attention. Um, I'll be going over causal attention, which is, and attention masks, which is the first kind of idea to add attention masks and to make this thing actually work in GPT models. Padding masks, so like in practice you need padding masks or else like it's just not going to work if you don't have it. Um, Sparse attention, again, you can mask your attention matrix and then graph representation from that. Cross attention, linear attention. So yeah, I mean, up to cross attention is kind of just normal transformer stuff. And then I'm going to be getting into more complicated things like linear attention, gradient-based attention, RNNs versus transformers, and then some interesting things that have popped up lately. MLP as attention and Mo as attention. Um, Basically going over a ton of stuff. So yeah, what's the point of this? So I mean, attention is basically the backbone of everything. Um, if a model exists, it's using attention, probably, in some way or another. I want to break it down in kind of an intuitive way. I have a way that I like to explain it, and I just want to talk about it that way. And then there's also some papers that have come out recently, like this, I think it was token form or pretension, which somehow got a spotlight, and it is an MLP. So I'm going to be going over at the end, how do you make this thing an MLP, and how do you make it into a light mo. So yeah, just so that that exists out there and so that there is not another spotlight that redrives an MLP and calls things QK and V. So yeah, a lot of stuff. This is going to be a long video. So yeah, assumptions. I'm going to be assuming you know a lot about the transformer already, except for the attention part. So like you have this embedding matrix, you have the positional encodings, you have the norm. I'm going to be assuming you know everything except for the attention part. Like the hardest part of the transformer is the attention part. That's like the hardest part to kind of understand. Um, it's not that hard to understand like the embeddings and stuff like that. But I'm not going to be going over that here. So like normal optimization, know that this is actually doing next token prediction and stuff like that. Um, because I won't be going over that here. So I'm just going to be going over the attention pieces. But I'm going to be assuming you don't know anything about attention. So, I mean, in the first place, why do you need attention? Well, these, if you just had feed forward layers, like let's say I have a bunch of tokens, if you just had feed forward layers, it would only transform each token individually, and the tokens can't communicate with each other. So if you have attention, it allows the tokens to actually communicate with each other. So that is why it is so important. And it's not too bad. It just seems complicated. It's a lot less complicated than it seems sometimes. So yeah, just make sure you know a lot about the transformer except for the attention part. And if you do know about the attention part, hopefully there's some other stuff later in the video that are helpful or that you haven't seen before. So what am I not covering? I'm not covering, like I'm only covering attention. I won't be covering the norms. I won't be covering the feed forward layers. I won't be covering the positional encodings. Positional encodings are a thing all in themselves with like rope and absolute positional embeddings. MLPs, that's just normal machine learning, and then optimization is just next token prediction. That's not a big deal. Um, yeah, so cool. Let's go on to start with just base attention, and then I'll build up from there, basically building everything from scratch. So first, there's kind of these three formulations I can talk about. They're all the same, but this first one here is like this global formulation, I'm calling it. Basically, you have a function of, attention itself in its like most general form is a function on this inner product of two matrices. So you have this A matrix, this B matrix, you do an inner product on those, and then you do another inner product on C. So it's just two matrix multiplication where the first matrix multiplication has a function around it, and then this you do another matrix multiplication. So I'm going to be talking about the second one mostly. This third one also exists. So in the second formulation, this is the one you normally see. F is your softmax function. Q and K, you take an inner product on those, and then you do another inner product on V. So Q, this is how I'm going to be denoting the sequence, mostly throughout the slides. Q is going to be a matrix of shape n by d. So n is going to be the sequence length, and d is going to be the dimension. So n tokens of size d. K is going to be m by d. V is going to be m by big D or little e. I think I use little e later on, but just it can be different in terms of the embedding size, and then O will be of shape n by d. So in the most general sense, Q is n sequence length. K needs to have the same dimensionality as Q, but it can have a different sequence length. And then V needs to have the same sequence length as K, but it can have a different dimensionality than Q and K. And then O will take on the dimensionality of V, and O will also take on the sequence length of Q. And I'll get more into that later. So you can actually add a batch and head dimension, but that's pretty easy. Like, you just add them here, and you just treat that like a batch dimension. So it doesn't really affect anything. I'm not going to be talking about this at all. I'm not going to really be talking about the heads. It's like an easy addition. It's just adding another, like, nothing communicates through the head dimension except post attention, but like, it's an easy addition. So anyways, yeah, let's talk about the intuition. So let's say we have some text, like let's say I have like this set of tokens, like the cat set on the mat. So you can think of each token as a word. However, in practice, it's not just a word. It's usually like a word piece. So for example, ing could be a token, but I'm going to be treating them like words just because it's easier. So imagine we have the cat set on the mat, and this will represent 6 tokens, token 1, 2, 3, 4, 5, and 6. So cat set on the mat. Now, what we want to do is we want to basically inform all the tokens of each other. So we need to give, say, the mat context of, like, what is this mat object? So if I were to give you the word mat, you could say, well, I know it could be a floor mat, but I also know it could be like the name of a person, or it could be the name of a person. You don't know if mat is a floor mat or if it is the name of a person until I give you more context. So if I say the cat set on the mat, you're like, well, yeah, obviously that's a floor mat. But if I just say mat, like, you don't know which one it is. And yes, I do know that. I think mat has 2 T's, but whatever. Besides the point. So also, like, we need to give all the other words context. For example, this word the and this word the are different, although if you just have the word the, they look exactly the same. So what we're going to do is we're going to first tokenize our sequence. Here, the cat set on the mat, and yeah, just normal tokenization. And like I mentioned before, instead of using, like, in practice, you actually use word pieces, but I'm going to be representing them as words. So we're going to have 6 tokens. This will be a so if I go back to our queries, this is an n by d sequence, or n by d matrix. So n will be 6, and d will be whatever our dimensionality is. So yeah, this is going to be our example that I'm going to use throughout the entire, or throughout a lot of the presentation. But yeah, as I mentioned before, mat could be a name or it could be an object, and you don't know what that is unless you have context. So the goal of attention is to kind of give words the context of the entire sequence, and it's going to do that through this kind of all-to-all communication. So here's our example. I'm going to be looking at the word sat a lot, but we do this for all the words. So let's say we have this sequence, and we want to inform the word sat of the information around it. So we have the cat set on the mat, and let's say the word sat, maybe it needs to know some information from the word cat. What is doing the sitting on, like, what's performing this action? Well, I don't know what's performing the action until cat informs me a cat is performing the action. And the word mat, I don't know what this action is being performed on until mat sends me information. So what we want is we want a way to take information from cat, take information from mat, combine that with the information from sat in some way, so that we get this vector that doesn't just represent the word sat, Like if I just said the word sat, that's not that informative. But if I have a vector that represents the word sat plus cat and mat, then that's a very rich embedding and you can do a lot with it. I also want to not get information from the word the or the word on because that's kind of useless. Maybe on is useful, but in this example, act like it's not. So an easy way to do that is to take a linear combination. So we're just going to combine all these vectors and we're just going to take a linear combination of them. So again, we want information from the word cat, we want information from the word mat, and we don't want information from the word the, on, or the. So maybe we still want this vector to represent mostly the word sat, but we want to have a little bit of information of the word cat and the word mat. So let's say we have values between 0 and 1 and add up to 1 to represent the new representation of the word. You'll see later, due to softmax, this is a assumption that is met. So what we're going to do is we're going to say I want 60% of the word sat, so 0.6 sat, I want 0.3 cat, and I want 0.1 mat. Maybe we still want the representation of the word sat, so we want 0.6 of it. We want to know what's doing the sitting, so we take 0.3, and maybe we're like, well, maybe we need more about what's doing the sitting than what we're actually sitting on, or what the cat's sitting on, so we weigh this one a little bit lower. It's arbitrary at this point, but we're doing this linear combination. And then we weigh the rest 0 because we don't want any information from those words. So yeah, this is our new combination. We have the word cat, or now we have this representation here, which is a linear combination of all the vectors here. So 0.3 times cat, 0.6 times the vector sat, and 0.1 times the vector mat. You add them all up, and you get your new representation, which now does not represent sat. It represents sat, cat, and mat. It represents 60% sat, 30% cat, and 10% mat. So that's the idea, and you do this for all the words. So this is basically the entire idea of attention. We're just going to do a linear combination of all the words for every word in the sequence so that you have this all-to-all communication. Every word gets context of every other word, and it decides how much of every word it wants. So for this example here, this is our sat vector here. Sat wanted information from on and mat. Well, in the previous example, I wanted cat and mat, but I guess here I put on and mat. Whatever. Let's say the word cat needs to know, I want some information from the word sat. I want to know what action I'm performing. And then mat, maybe it needs to know what's the thing sitting on it. I don't know. It's arbitrary. So every vector is a linear combination of every other vector here. Side note, we're going to be treating this as a causal representation later. And what that means is that every word is a linear combination of all the words up to that point. So the word the would be a linear combination of just the word the. The word cat would be a linear combination of the cat. And the word sat would be a linear combination of the cat and sat. And so on. Like the word mat would be a linear combination of all the vectors. So this is what we mean by causal. It just means that if we have a sequence of text or a sequence, the current token only gets information from the tokens up to that point. So I'm going to be talking about this later, but side note and a diagram to kind of represent, to show that. But for now, we're going to treat this as all-to-all communication between all the vectors, and every vector or every word can get information from every other word. So another side note is with tokens, you can represent pretty much anything. If you can tokenize it, you can treat it as a sequence or a set and throw it into attention. So tokens are basically anything that like you basically have something that's bigger and you break it up into a bunch of tokens. It can be a graph, or it can be an image. For example, the way you represent images is by tokenizing it, and the way you tokenize it is by patchifying it. And by patchifying, I mean you just take non-overlapping patches. They can be overlapping if you want, but it's easier, like if you wanted a causal representation, then you wouldn't. But you take these non-overlapping patches, throw them here, and each patch you can flatten. Like, let's say this is 128 by 128 pixels, then this would be a 64 by 64 matrix here. So you can flatten that matrix and you get a vector. You can throw that vector through an MLP and you get a representation for this patch here. And that would be of dimensionality D, whatever that dimensionality you want that to be. So this is how you represent images now. You used to throw them through a convolutional neural network. Now you tokenize them and then throw them through attention. So you can tokenize anything, or if you can tokenize it, you can throw it through transformer, and you can tokenize most things. Um, yeah, so self-attention. Basically, self-attention is going to be, that's going to be the first thing I go over, and then I'm going to be going over bidirectional self-attention at first, but we'll build from there to causal attention and to cross attention. So again, these are our formulations here, and I'm just going to be talking about this middle one here. You can add batch and head dimensions, or you can treat it like this. I'm going to be using the middle one because that's the most common. But yeah, let's just go over the dimensions real quick. N, the number of vectors in your sequence. D, the dimensionality. D1 here, or big D, is going to be the number. Wait, no, that's M. M is going to be the number of dimensions in the first projection, or it's going to be the number of tokens in our second sequence. And D2 is going to be the output projection. And basically, you can also interpret this through an attention perspective, where N is going to be, where we're actually going to replace M by N. And once we replace N by M, you get self-attention. So treat this M like N and treat this D like little d. Then all we have is we have N and M are our sequence length, and D is going to be our dimensionality. We'll get to we'll get to actually using this M later, so it's just N, all the same size matrices. So, yeah, how do we do self-attention? So you do that by this formula here, and this formula is, I mean, so I removed a part right here, a denominator right here. That's just for normalization. Don't worry about that part. But this is essentially your self-attention, or your into all your attention representations. So here are queries. So this is an n by d matrix. Here are keys, d by m, and v. Our values are m by d, and we're going to be throwing it through this. So don't worry. Looks scary. We'll break it, or we'll go through it step by step. So the first thing we need is, looking at this representation, is we need our queries, keys, and values. So, oh yeah, and a side note on softmax, it is a lucky choice of function that is fantastic. Try to come up with a function that's better than softmax. I guarantee you cannot. And if you do, write a research paper about that. That would be awesome. Anyways, so what we first need is we need our queries, keys, and values. So we have our input here. So the cat set on the mat, this is just our tokenized representation of our text. So this is an n by d matrix. What we're going to first do is we're going to project this 3 times. So we have 3 MLPs, or 3 weight projections, WQ, WK, and WV. These are simple linear projections. Maybe you have a bias, so affine transformations if you want to be fancy. But we have 3 linear transformations, and this will form 3 different representations of our data: queries, keys, and values. They could be the same if these transformations were the same, but these are going to be learnable, and they probably won't be the same. They have different gradient functions, so they're probably not going to be. Each of these are going to be n by d matrices. So since this is a d by d projection, literally all you're doing is you're transforming every token through this matrix to get a n by d representation here. So all this does is it transforms every token, and yeah, new representation, query, keys, and values. Again, those are n by d, so the dimensionality doesn't change. It can if you want. I'm not going to change it here for simplicity. So first thing we do, transform these. Second thing we want to do is we want to do these linear combinations. So looking back at our example, we had this here, where the word sat was transformed by taking a linear combination over all of these vectors here, by taking 30% cat, 60% sat, and 10% mat. So how do we do this? We're going to do this using good old attention formula. So I'm just going to be looking at the word sat right now, but we're going to generalize this to every vector by just doing this multiple times. So first thing we're going to do is, real quick, I'll go back to the formula. This is what we're going to be computing in the end. So inner product, softmax, inner product on values. That's what we're going to be doing step by step. We're going to do QK transpose, and then softmax, and then the values. So let's go back here. First, we're going to do QK transpose. So Notice how we're doing this. We're doing an inner product, so q sub t is going to be, well, in our case it's 3. So I'm just going to be looking at the sat token. So the sat token is the third one in our sequence, so I'm going to be looking at q sub 3, or q3. And what we're going to do is we're going to take q3, this is a vector, and we're going to multiply it with all of our keys. So this will be qt k transpose 1 to n, where this is our sequence length and we're doing an inner product on every single key. So we have one query, inner product with all the keys, and this will give us a scalar for every single one. So if this vector here is of dimension d, because we only have one vector, and k transpose is of dimension d by n, because we have n vectors of size d and we transpose that, then this output matrix here, or this output vector here, will be of shape n, where each of these is a scalar representing the inner product between the query we have for sat and the vector for every single word. So notice this one here is sat inner product of q sat and kv. And you do that for all of your words in your sequence. This is annoying to write it out in PowerPoint, so moving to LaTeX, which is what I should have started with earlier. But yeah, you just do an inner product of q3, which is sat, with every other key. Second thing, exponentiate that. So you exponentiate this inner product, making it a value between 0 and infinity. So this is a scalar, you exponentiate that scalar. That's just the first part of softmax. So we did the inner product, now we're exponentiating it. Then what you do is you multiply it by the values. So we're actually going to add them up, but first we'll just multiply it by the values. So what we have is we have the inner products. So this will be a vector of size n, where n is 6 in our case. We exponentiate that. This will still be a vector of size n, simple exponentiation. Then what we do is we multiply it by the values. Notice how the keys and the values share the same index. What we're doing is we're basically taking this scalar and we're just multiplying it by every vector. So this is a vector of size n, this is a vector of size n by d. Where each vector here, so v1 is going to be a vector of size d. This vector here represents the word the. This vector here represents the word cat. This vector represents the word sat, on, the, and mat. And we're multiplying it by each of the scalars. So remember how before we had the word sat, and we wanted the word sat to be a new representation, a linear combination of all the vectors in our sequence. Basically what we're doing is we're saying these are going to be our weights here, the exponentiated inner product of q and k, and these are going to be the vector representations that we're combining. So you'll see that come up in a second, but essentially what we're doing is we're creating weights by exponentiating the inner product, and we're weighing all the values, which are going to weigh each part of our sequence, each vector, and then we're going to add them up. So here, I just did a sum, like I should have done a sum earlier because this is an inner product, but yeah, this is what you have here. So basically what we did is we did inner product of q3, query for sat, inner product with all the keys. That's the first thing we did. We exponentiated that, and then we multiply that by the values. So this is what we have here. So before, again, remember how we did a linear combination of the cat sat on the mat, where we had a weight and we had all the vectors. So again, you can see that here. Imagine every a is our weight that we computed, and every v is our vector, the values that we're going to be combining together to form this new representation of the word sat. So that's what you can see here. And again, the weights are coming from the inner product of our sat vector, the sat query, and every word in our sequence. So this slide is representing that. So A is our weight, V is our vectors. And then what we do is we normalize this for softmax. So all I'm doing here is I'm taking this representation, adding up all the A values, and then dividing by that. So that's softmax. The normalization part it is important, but for the sake of explaining how it works, it's not that important. Basically, it just makes sure the weights add up to, or are between 0 and 1 and add up to 1. But for the sake of explanation, it's not too important, and this is the most important part here. It's a linear combination of these weights. So yeah, this is what we can see here. Notice how the So this is the full equation here representing the output of the word sat. So notice how we just take the queries from sat and we take the keys and the values from all the other words. Again, what we do is we take these queries, we do the inner product on all the keys to give us our weights. We exponentiate those weights, and then we multiply them by the values. And you have this norm here so that the weights are between 0 and 1 and add up to 1. And again, these weights are scalars. They define our linear combination that we're going to create for all the words in our sequence, and these values are vectors. So yeah, hopefully that makes sense for how we're getting it. It's literally just what I showed before, just in a more complicated way with these exponentials and this norm denominator. So yeah, that's what we're going to be doing. Just linear combination of all of our words for every word. And we do this for all the words. So this is just the equation for the word sat. So notice how the queries basically define the output here. You do this for all the other words. So let's say we wanted to do this for cat. We would replace the query with the query for cat. And what this does is it takes the query for cat, it multiplies it by the key for every single other word, and it does a linear combination of every other word by adding up the values for all those words. So exact same idea for every other word. We just replace the query. And if you do this for all your queries, then you get the attention. You get what you have for your attention. So yeah, I mean it's basically just creating weights and doing linear combinations of your values. So we can represent this in a attention matrix. So that's what you can see here. What this attention matrix represents is the inner product on your queries and your keys. So what we had before is we had just this row here, qsat or q3 multiplied with all the keys. So we just had this row here, essentially. This is the representation for all the queries. So this represents the weights we're creating for every single combination. So this here represents the weights we're creating to combine all the vectors for the word sat. This here represents the weights we're creating for all the vectors for the word cat, and this represents the same for the word the weights for the word the. Now, when I say weights, you may see these as either the softmax value. So to make this a softmax value, you would exponentiate these and then divide by the sum along the row. Or you can see them as pre-softmax, where it's just the inner product. So you can see either of those out online. And the way you can read this is, as I described before, every row represents the weights for that row, where it represents the weights you're going to be combining the values with. And every column represents basically how that word is going to be sent to all the other words. So you can think of it this way. These are keys, these are queries. So you can think of it as information flowing from the keys to the queries, or from the keys and the values to the queries according to the weights defined here. So for example, we could have weights that look like this. So what this is saying is the word the is just going to have is just going to take the value from the. Not interesting. The word cat, on the other hand, it is going to take 80% from the word cat. It's going to take 10% from the word sat and 10% from the word mat. So this is our linear combination here. For the word sat, like we had before, it's going to take 30% from cat, 60% from sat, and 10% from mat. So literally what this row is representing is it's representing the attention weights that we have, and the attention weights are formed from the softmax on the inner product, where the softmax is performed along the row. And what this represents is how am I going to weigh every single value. So this represents how am I going to weigh the value the. That's what this column represents. This column represents how am I going to weigh the value, or the value cat, that vector, for every output here. And this represents how am I going to weigh the vector sat for every for every input into my attention, which is also going to be the output. So yeah, that's what you can see here. Now, to show exactly what this represents, basically give the big picture about this attention matrix, because this attention matrix is very important. You're going to see this everywhere. It basically represents two things. So along your columns or along your rows, you have your queries, and remember how I said before, your queries are defining your output. So this represents the queries and the outputs here. I drew them, I put them on the right just to kind of show flow of information going from left to right. But yeah, I mean, it's a row, so it's also a sum, so you can change it around. The columns represent the keys and the values together. So basically, every weight represents the softmax value of the inner product of the corresponding querying key. And then you weigh that by the corresponding value in that column. So for example, let's take this column here. This value represents the inner product of Q1 and K2, so 0. This one represents Q2 and K2. This one, Q3 and K3. That's what these weights are representing. Now the value V2 is going to be multiplied by 0 for the new representation of the word the. It's going to be multiplied by 0.8 for the new representation of the word cat, and it's going to be multiplied by 0.3 for the new representation of the word sat. So that's what the columns are representing. The columns are representing the keys and the values. Now, again, the rows are representing the queries and the outputs. So let's just look at this row here. So, like I defined at the very beginning, we want to define a new representation for the word sat as a linear combination of all other words. So I'm using the exact same weights as I had before, where these weights come from. This weight here comes from the inner product of Q3 and K2. So the query for sat and the key for cat. And it comes from exponentiating that and then dividing by the sum of the row, of all the weights in the row, thus the softmax. And then we're going to multiply that by V2. So you can see here, O3 is defined by this, where every single one of these is the corresponding weight. So notice I only have Q3 because I'm only taking it along this row, Q3 all along here. And then we have K1 V1, which represents this weight here along with V1. K2 V2 represents 0.3 and V2. K3 V or Q3 Q3 K3 V3 0.6 and V3, and so on for the rest of the row. And you can see here, I translated this would actually be a softmax, but I just put the exponential there. But it's the softmax along this row, and you can see here, these are the corresponding weights. This one should be 0. I'll fix that. This one should be 0, not 0.1. 0, it's 0 here. This one should be 0. But yeah, these are the weights that we have in this row here, and we just do our linear combination as I mentioned before. So here we go, linear combination. Yeah, that's what this is representing. So hopefully that makes sense. This is kind of the basis for the rest of the presentation, so hopefully you understand how attention is working better, and what this matrix is looking like. This will be important for masking. And what we can do is we can take this attention, so the output of attention 1, and then we can just do a linear combination of them. So this is just one attention head. That's what it's called. It's called an attention head. And what you can do is you can form attention, say, h different times in your h different times. So imagine I have a sequence, the cat sat on the mat. This one here would represent one way of combining all the words. This one here would represent a different attention map. It would represent a different way to combine all the words. Attention 3 would be, yet again, a different way, where each attention 1, attention 2, and attention 3 have different query key and value projections. And that allows it to define a different linear combination, and yeah, it's basically doing attention multiple times in parallel. And then what we do is we combine all these attention outputs. So yeah, each attention output is going to be of size n by d, and you just do a linear combination of all those along the heads, where in this case we have 3 heads, so every head is just a parallel attention computation that you're doing. and you multiply by this weight, so you take this linear combination of these attention outputs and you get your output for your multi-head attention. So whenever you see multi-head attention, all you're doing is computing attention multiple times in parallel, where the query key and value weights are different, and then you're doing a linear combination of all those. So it allows it to do more complex things with attention. Yeah, so I think that's everything for self-attention. Again, that's the basis of the rest of the slides, so really make sure you understand that part. It's just defining a linear combination of the values, essentially. Now what we're going to do is we're going to define causal attention. So remember before, if I go all the way back here, how initially I said we're going to take a linear combination of every word. Well, now what we want to do is we want to treat this in a causal representation. So I'll get to why in a second, but what that, again, to remind you, means is every word is a linear combination of itself and all the previous words. So the word sat would just be a linear combination of the cat sat. The word on would be the cat sat on. It doesn't take into account any future values. So let me go back here. So we've only talked about bidirectional attention, and this means every part can receive any other part, so it's an all-to-all communication. So what we're going to do is we're going to start introducing attention masks, and attention masks are, it's a way to remove parts of the attention matrix. So here, attention matrix, and it allows you to do things, a lot of things, and we'll go over all those things here, or a lot of them. So causal attention motivation, let me explain why you would only want to get the past and the present, I guess. So in our transformer, if we're doing next token prediction, imagine we have the word sat. So again, we're looking at the word sat. This is the attention formula here for the row of sat, where we're computing the weights. We're multiplying it by the values, and we're dividing by all the weights here. So normal attention, this is what I showed before. So this is what we want to do. We want to combine information to sat. So we want the new representation of sat to be this combination that is informative of how to predict the word on. Now there's a problem here. An easy way to do that is just to remove every single value except for on. Then it's really easy. All you have to do is copy and paste this, and there you go. There's your prediction. So yeah, that's too easy. All you need is one attention layer to do that. That's not hard. You don't need a whole transformer. This isn't what you want. So there's a problem with this future looking ahead for next token prediction and for causal tasks. So what we really want is we want to remove all the future values so that the model cannot cheat. So during inference, like this is fine. This is fine to do. You're going to get an amazing loss. It's going to converge to practically zero. Fantastic. However, during inference, if I were to produce the cat sat on the mat, let's say I were to give you the sentence the cat sat, or I were to give the model this. The model can't pull information from the word on. However, the model was trained to pull information from the next token, but during inference it doesn't have that. So this is a problem. We want to stop the model from cheating. So to do that, we remove all the future information and make it causal. So that's why we need attention masks. So as you can see here, we only have information up to the word sat, no future information. So basically stop the model from cheating so that we can do inference with it. So introducing the attention mask. This here is an n by m matrix. So remember, queries are n by d, keys are m by d in the general case, and values are m by d in the general case, where in self-attention these were n, where m was equal to n. So this is a general case, but m is equal to n in the self-attention case. So m is going to be an additive mask on the queries and the keys. So add it, and then we apply softmax, and then we multiply it by the values. I'll show you what this does. So yeah, it prevents routing of information somehow. So let's look at this. So introducing a tension mask. What we're going to do is we're going to define this mask. Again, this is a n by m matrix where in the self-attention case, it's n by n. So here's our n by n matrix. Now, this is going to be our mask that we're defining. And what we're going to do is we're going to define a mask that is not binary. It is full of zeros and negative infinities. I'll explain why it's a negative infinity in a second, but this is our mask. So again, I have this reminder here. Reminder that this is essentially sending information. Our keys and our values are sending information to our queries. What this represents is 0 means I want you to route information, and negative infinity means I don't want you to route information. And you'll see why in a second, but this is a very easy way to look at it. So let's see the word cat. The word cat in the normal case can take information from the cat sat on the mat. Now, what this mask represents is it says cat can no longer get information from the and mat because we have negative infinities here. So that means cat is only a linear combination of the cat sat on. It doesn't have any information of the or mat. Well, for this the, not this one. So that's what this is saying here. And remember, this is every row represents the linear combination for the word represented here. So we're going to be looking at this pretty much row-wise because every row defines an output. So this is again the output. Here I'm going to look at the first row. Instead, I'm going to be looking at the word the. So if we just look at the first row, let's say we have this here. So let's say the values that we produce are 1, 2, 3, 4, 5, 6. So we do an inner product, Q1, with all the keys. So Q1K. This gives us a linear this gives us a inner product for the word the with all the other words for all the queries, and this gives us a weight. I just picked 1, 2, 3, 4, 5, 6 because that was easy, but usually this represents weights that are important. So these are just not random weights. These are just weights I picked. Here, this represents our mask, and what we're going to do, again, as the formula shows here, all we're doing is we're adding this mask. So we're taking this mask and we're adding it, as shown here, it'll be 0, 0, 0, 0, negative infinity, negative infinity. So we add that here. We add that to the rows, and anything added to negative infinity becomes negative infinity. So what you get here is you get 1, 2, 3, 4, negative infinity, negative infinity. So qk plus m. Now what we do is we exponentiate that, and once you exponentiate negative infinity, it becomes 0. So you effectively have masked out this value here by making it negative infinity. If I made it 0, on the other hand, it would become a 1, and you still get this attention weight. V would no longer have a value of 0 weight, it would have a value of 1 weight, which means we didn't mask it. So this is why we have negative infinity. I used base 2 because I didn't feel like having exponentials, but whatever, you get the point. You exponentiate negative infinity and you get 0, and this gives you this here. So 2, 4, 8, 16, 0, 0. Exponentiating negative infinity gives you 0. So that's why we use negative infinity and 0, because if you add 0, it doesn't do anything, but if you add negative infinity, it masks it due to the exponential. And then this is just dividing by the denominator, and if you divide by the denominator, 0 divided by anything besides 0 is 0. So yeah, that is that. And that is the reason why you do this. So mask by negative infinity so that the negative infinities become zeros, and then you have 0 weight. So why not just multiply by 0 and 1? So we will actually do this later with linear tension. But the reason you're going to do that is because you have this exponential on the inner product. So what if we apply a binary mask after softmax? So what if we did qk transpose softmax and then we multiplied by m? Like this matrix here is an n by m, or is n by n. Why not just multiply by binary mask after? So there's a problem with that. And the problem is the denominator. So if we have a binary mask that we multiply after we compute the softmax of the inner product of their queries and keys, the problem is the denominator still carries information from the values we wanted to mask. So if these did not become 0, if these were some value that were not 0, so whatever value we had before, 5 and 6, this would be 32, this would be 64, the sum the denominator would carry 5 and or would carry 32 and 64 in it, which means these values are divided by 32 and 64, or are divided by s with 32 and 64 in it, and then you mask it. And what that means is that there is this information leakage, and that means that there is still this, like, you didn't really mask it, and the gradient will treat it like you did mask it, but you have this information leakage. So our desired sum is a1, a2, a3, a4. However, what you get in the denominator is a1 to a6. So binary mask bad. You don't mask the denominator still. If you mask the denominator, then it's fine, but just add negative infinity and 0. So what if you apply a binary mask before the exponential? So as I mentioned before, if you have 0, so like let's say we multiply it by zeros and ones instead of 0, you multiply it by 1 instead of negative infinity, you multiply it by 0. If you did that, you would get a 1, which means you still have a routing of information. It's not a lot, but it's enough for it to cheat still. It will figure it out. If you don't get masking right, the model will cheat, you will get 0 loss, and you will not have a fun time during inference because it will produce garbage. If the model looks too good, it usually is too good. So if you're like, it's converging so fast compared to all my other models, it probably is because you messed up the mask. I know that from experience. I've messed up the mask many times. So, reasons to mask. You can make attention causal. You can prevent tokens like padding tokens from sending information. We'll get to that. You can simplify the attention matrix, and you can make weird attention patterns. There are a lot of reasons you can mask it. Is it the most efficient way to stop information from flowing? I don't know. I just multiply things, and the CUDA kernels do the rest. I'm kidding. But so causal attention. Basically, we have this way of masking things, and we want to mask it such that we have this causal representation. So how we're going to do that? We basically want, again, to reiterate this. We want only words to affect itself, and words, so we only want words to be affected by itself and words in the past. We don't want it to be affected by words in the future. So the cat set on the map, we want the word the to only affect itself, we want cat to be affected by the cat, and we want sat to be affected by the cat and sat. So again, that's what we want. We don't want it to get information from the future because that causes problems. So this is our attention mask. Let's go the causal attention mask. So here, this row represents the word the, so the can only get information from the word the. So the cat sat on the mat, and again here. This one represents the word cat, and it can get information from the and the word cat. This one, the word cat, so cat can get information from the word the, cat, and sat. Wait, no, this is sat. Sat can get information from the, cat, sat. And so on. Notice how this last one here doesn't have any masks in the row, and then that means it can get information from every other word. So we define this upper triangular of negative infinities, and the rest are zeros. And then we add it. So we add that here to the matrix that we had before. Queries, keys, the cat sat on the mat. And again, here is just another upper. This is just adding this mask to the attention matrix. So notice we only take the inner product of Q1, K1. Here we take the inner product of Q2, K1 and Q2, K2. So output 1 is basically going to be 1. It's only going to be itself, but output 2 will only be a combination of these. So there you go. Yeah, so once you apply softmax attention, or once you apply softmax, you get a value of 1 here. Special case for the first one, and for the rest you get these attention values here, where these attention values are only up to the current token. So that's why it's only up to the diagonal, because the diagonal represents the self, the token, basically the token attending to itself, while below the diagonal you have tokens from the past sending information to that token. So here, output 1 is only a combination of v1, output 2 is a combination of v1 and v2, output 3 is a combination of v1, v2, v3. I reiterated that a bunch, hopefully it makes sense. Basically, only taking past, where the past is backward. And we represent that through the attention matrix because it's easy. So causal attention. And my notation here basically says this is the query, this is the row, and the second value is the column. So causal attention, so this is only required for training. So if you really wanted to, like if we really wanted to not have a causal attention mask, you could iterate token by token. So I would take the word the, I would pass that through the entire transformer, and I wouldn't need a causal attention mask because it would only be this value here. And then I would backpropagate, I would then pass in the and cat. So the and cat would only have this box here. It's 2x2 matrix. And in this case, you don't need, if you're only modeling the word cat, you don't need the causal mask here at all. And you can send that through your transformer and backpropagate. However, in the normal attention case, like if you do add this mask, it allows you to do one forward pass for every word in your sequence. That is fantastic. A forward pass for every word doesn't get much better than that. If you do it without the mask, you have to do a forward pass for every word in your sequence. So one takes one forward pass and has an attention mask. One takes a forward pass for every word, which is just intractable in practice. So you add this attention mask. One thing to note is that the attention mask actually does remove information. So if you add this attention mask here, it is a trade-off because it does not allow words to send information backward. So you get this problem where words can only send information to the future, but the future cannot send information backward, and that's good for efficiency because we can send all words in at the same time. But it's not good if you need to send information backward in your sequence, which is sometimes a good thing. So it's this trade-off you have, and there isn't really a good way to fix it where, like, good research problem, if you're looking for some research, get this transformer to work in a bidirectional way so that it can send information backward without you running into this cheating problem that the model has. So side note there, but I think there was actually a paper recently, but it's not trivial. So yeah, causal attention. Padding mask. So hopefully that made sense. Basically, you add this mask, information can only flow from the past to the future. Padding mask. So let's say I have two sequences. So in reality, you're going to have a bunch of sequences. They're all going to be different lengths, and that is annoying to deal with. So let's say I have the sequence, the cat set on the mat. Let's say I have another sequence, I like pie. Now, I could pass sequence 1 through the transformer, backpropagate, get my, and then I do the same with sequence 2. Pass that through the transformer, backpropagate. That is inefficient, so what I want to do is I want to batch these. So the way you batch these is you concatenate them. You concatenate them into a new dimension called the batch dimension. Now there's a problem here. You can't add another, like let's say I wanted to, not concatenate, you stack them. You can concatenate them. I'm not going to get into that here. I forget what the paper's called, where you concatenate them along the sequence dimension. So you can actually concatenate them along the sequence dimension, and it requires a different padding attention mask. But we're going to be stacking these together. So I want to produce a batch dimension with these two stacked together. Now, if this has 3 words and this has 6 words, I cannot stack them together. You can't have a matrix that is, like, if I want to create this tensor, and I want this tensor to be of shape 2 by something by d. I need that something to be the same length. I need the sequence length to be the same for both sequences in order to create this batch dimension. Now, what you can do is you can pad sequence 2. So we can pad sequence 2 such that it's of length 6. Then we can stack these together and form a batch of data. So you couldn't do this before because you can't have two different, like, if you're using normal tensors, you can't have two different size tensors and stack them together. That's not how it works. You can't do that in memory, or you just can't do that. It doesn't make any sense. So you add padding tokens, you stack them together, and you get this new batch. You get this batch here. So cool. We've solved the problem, except you didn't solve the problem for attention. So this is what we have. It's fine for sequence 1. Sequence 1 is fine. You just send it through, you're going to send this batch through your transformer, and this transformer is going to treat each sequence independently. It's going to create an attention mask for sequence 1, or an attention pattern for sequence 1, and for sequence 2 independently. It's going to be stacked together, so they don't interact. It's just efficiency reasons to create this batch dimension. Now, here is where the problem occurs. It occurs in the smaller sequence, or smaller sequences if you have a larger batch. Yes, here we have the attention matrix, and yeah, so we have the padding tokens here. So I like pi, pad, pad, pad. I like pi, pad, pad, pad. So this is our self-attention matrix. Now, during inference, you will not have padding tokens, and the problem here is, again, we have our keys sending information to our queries. So the problem here is the word I will be a linear combination of not just I like pi, but it will also be a linear combination of these 3 padding tokens. These padding tokens are useless. They're not going to be there during inference. Well, they probably won't be. You don't want information from them. It's just like, it's not as bad as having a future, like a problem where it takes information from the future, but it's pretty bad. You have these padding tokens. They shouldn't be there. They're not going to be there. And if they're not there during inference, they shouldn't be there during training. So what do? We mask them. So we mask them like this. So we mask them along the columns. Now, think about that for a second. Why do we mask along the columns and not along the rows? Now, the reason you do that is because, remember, the keys send information to the queries. So what this is saying along row 1, we are not going to have the word I be a combination of any of the pad tokens. And the word like is going to be the same. It's going to not be a combination of the pad tokens, and so is pi. Now, what about the pad tokens themselves? Well, since we don't care about the pad tokens in the first place, they're just there to pad our sequence, this padding token, it doesn't matter what information it gets. It's not going to be modeled in any way. As long as it doesn't send information to any other words, it doesn't matter. As long as it is not, like, it doesn't have any values up here, that means it's not sending information to the words we actually care about, then it doesn't matter what it becomes. So we could mask these as a negative infinity. However, one, you run into softmax issues. The softmax of a row of negative infinity is undefined, because it's just, yeah, it's undefined. But second, it also is computationally inefficient because you don't care about the linear combination of this row here. Again, this padding token can be whatever it wants to be. You can transform this in any way as long as you aren't modeling it. And as long as it isn't sending information to the rest of the sequence, it doesn't matter what it's doing. So this here is transforming pad. Doesn't matter what it transforms into. We can send it the word I like pi, and it doesn't matter at all. So that's why we pad along the columns, so that these tokens don't send information to these tokens here. That's the reason. If you pad it along the rows, then this part here, like, you would only have padding tokens that, like, the padding tokens would just be negative infinity and it wouldn't do anything. The information from the padding tokens would still be sent to I like and pi. So, yeah, that's why you pad along the columns, not the rows. Columns, you prevent information from being sent from keys to queries. Rows, you prevent information from being sent at all. So, causal mask and padding mask. So let's say we have a causal mask, normal upper triangular causal mask, padding mask. Let's say we mask K5 and K6. Here, we mask K4, K5, K6. Here, I'm just masking K5, K6. We can combine them. So let's say we have a causal representation, like a causal model. We can add the padding mask to it. And what that says is K5 and K6 are padding tokens, and the rest of the sequence needs to be modeled in a causal way. You could see why you may want to do that. If you were doing a GPT model, you would use this mask here, or whatever, up to whatever padding goes to. So yeah, that is that. So causal padding mask here, basically two things. You prevent words from the future attending to words in the past, and you prevent pad tokens from attending to the rest of the tokens here. Pretty self-explanatory. You're just adding the two together and it works because negative infinities do their job. Yeah, so hopefully that makes sense. Causal mask, you prevent words from the future from sending information to the past, and padding token or padding mask, you prevent padding tokens from sending information at all. This doesn't send information anywhere. So sparse attention and graph representation. Real quick, I just wanna mention this. It's not too important unless you're dealing with obscure data. But if you're dealing with text or images, you're not going to be dealing with this at all. Well, maybe. So let's play with the mask a little bit. For example, what we can do is let's add some sparsity to this. And the reason you would want to add sparsity is because it is more computationally efficient. Why that is, go play around with CUDA a little bit. Well, basically, it only allows you to compute a part of the attention matrix. So instead of doing QK inner product, you only have to compute some of the values. And that can, one, be more memory efficient, and two, be more computationally efficient. However, it is less expressive because you don't get this all-to-all communication. For example, let's do this thing called sliding window attention. Sliding window attention basically says, so the diagonal is the attention from a token to itself, and one off the diagonal is saying the token before me can send me attention, and one off the diagonal to the right is saying the token after me can send information to me. So what if we define a sliding window of size 3? And a sliding window of size 3 is saying the token previous can send me information, and the token after can send me information, but no other tokens can send me information. Those are negative infinity. So you can see here, if we take Q3, which remember was sat, it can take information from cat, and it can take information from on, and it can take information from itself, but nothing else. So sliding window attention, you usually define this to be a large window of size like 512 if you're modeling real long sequences. Now, there's a problem here, and the problem is you don't get this all communication. It doesn't know anything about the word on and mat, or the mat. So it's a trade-off. If you think locality is more important then this could be useful. However, I think in modern BERT you actually have a combination of the two. You have global attention and local attention. And local attention, or this attention pattern here, sliding window attention, you can think of that as a convolution across time. So here you can see this window here of size 3 just sliding across time, and you can think of it as a convolution because it is. So why would we do this? Maybe not all the attention is necessary. It's more computationally efficient, saves memory, and again, it is used in modern architectures sometimes. Research question: do you need all attention all you need, or is some attention all you need? Apparently, if you have a mix, as in modern BERT, it does quite well, and it's fast and computationally efficient. However, if you only have sliding window attention, it sucks. It's not that good. So, yeah. I don't know. Go look at some research papers. Or so this is from Longformer, and basically they define sliding window. They define their attention as a combination of a bunch of different attentions. So here, full attention. The white boxes represent a mask of negative infinity, and the green boxes represent a mask of 0. So you can attend to green, you cannot attend to white. Again, this is the attention matrix shown in a lot of places. So what this represents is, as I said before, you can only attend to only the neighbors can send information to you. In this case, this is the neighbors. This is size 7, so the past 3 and the future 3 can send information. Here, this is dilated. What if you do the same thing, but except you skip one? Same thing as convolution. And here, this is saying, let's say we have a classification token. Maybe that token is really important. If there is a really important token, we want that token to, 1, send all information to it, so it can receive all information from every other token. Thus, the row is completely green. But it can also, the row is completely green. But it can also send information to every other token. Thus, the column is also all green. So yeah, maybe you have important tokens that need all attention. They basically define a combination of these two by saying, what if we define global attention and sliding window attention? How well does that work? It's okay. It's not as good as full attention, so you don't get this all-to-all communication, but it's fine. It does work. just not as good. But it exists, and I wanted to talk about it. So these masks allow you to create weird patterns like this. Graph representation. So let's represent this as a graph. I think this is right. Maybe I. Yes. No, this is full. I don't. This should not be masked at all. Yeah, this should not be masked at all. There should be zeros here. Pretend like these are zeros. They are not negative infinities. The mask comes later. It doesn't come here. So pretend these are all zeros. Again, I'll fix that. This is a long presentation, so bear with the few issues that I didn't see. So these are zeros. This is the graph that you see if you have a full attention matrix. Again, zeros, not negative infinity. So you can create a graph, and the graph is basically this bidirectional graph between all of your. If you define every node to be a word or a token, then you can define this graph, where this graph is a fully connected bidirectional graph. Again, these should be zeros. They're not here, but what that represents is this fully connected graph here. Now, if you add a attention mask, so not this mask should be all zeros. This should be the actual mask. It basically either removes nodes. So, for example, between mat and sat, it removes edges. If you define negative infinity on both mat to sat and sat to mat, but it also defines unidirectional. For example, on and cat. So on can send information to cat. So if we look here, remember keys send information to queries. Queries receive information from keys. So on to cat. Here, this is 0, meaning we don't mask it, but cat and on is negative infinity, meaning cat cannot send information to word on, but on can send information to the word cat, as seen in this arrow here. Same for on and sat, and we also remove the insat here. So yeah, attention matrix basically defines, like you have this graph from the attention matrix, this bidirectional fully connected graph, where edges are, it's not hyper edges, it's just normal graph, first order edges, defining pairwise relationships, and defining an attention matrix, or this attention mask is essentially removing some of these edges and making them unidirectional. So yeah, that is another way to look at it, and it could be useful. These applications are more obscure, but it does exist. Cross attention. Okay, this is a big one. So cross attention, what happens? Basically, we have self-attention. Self-attention models it models tokens communicating with itself, or communicating with the sequence. So within that sequence. So tokens are combinations of other tokens in that sequence. But what if we didn't want to do that? What if we wanted to basically take information from another sequence? How do we combine two sequences? This is non-trivial, but it is easy if you do cross-attention. And this is where the M comes in. So what we're going to do is we're going to swap out the keys and the values to be from a different sequence. And we're going to keep the queries from our sequence that we want to model. So we'll go through that step by step. For example, let's look at the original transformer. So the original transformer has 3 different types of attentions. I say type for lack of a better word, but it has 3 different attention types. This is causal, or masked, if you want to call it masked. This is bidirectional, and this is cross attention. So let's say we wanted to define a translation from one language to another language. This will be our input. This is bidirectional because we have the entire input sequence. But the output sequence we want to decode word by word. So this is causal. Now what cross attention does is it says I want to add information from this sequence into this sequence here. And that way we know what to decode. That is what cross attention does. So here, this is language 1, this is language 2. We're sending information from this one to this one. And usually you hear that condition. So in the language of conditioning, you condition the sequence we're decoding, so language 2, on the sequence from language 1. And that is what we're going to do here. Note that the information is coming from this sequence and being put into this sequence. This is not a symmetric operation. It is very much not a symmetric operation, and you'll see why in a second. Another example is maybe you want to condition image tokens. So let's say I'm doing stable diffusion. You would want to take your text and you would want to condition your images on that in some way. So imagine your encoder is some text encoder and your decoder is your image decoder. You would want cross attention so that your text tokens can send information to your image tokens. Another example. So anytime you have one sequence and you want to condition it on another sequence, you use cross attention. So that's what we'll be doing. Now, in this example, I'm going to be translating the Spanish sequence here to this English sentence. So this is going to be our input sequence, and this is going to be our output sequence. We're going to take this, we're going to encode the whole thing, and we're going to use cross attention to send information from this encoded sequence to this sequence, so that we can decode this one word by word, but getting information from this sequence here. So notice how this is of size 6 and this is of size 7. That means like the dimensions are a bit strange, and it's kind of non-trivial to do this attention. So how do we do this? Remember from normal self-attention, we have Q, K, and V. Q, K, and V come from projections of our input. So our input is the cassette on the mat. We project that 3 times and we get Q, K, and V. Now for cross attention, we're going to change that. What we're going to do is we're going to create K and V from our second sequence here. So remember what we want is we want to, well, remember in our original definition, we have queries, keys, and values. Keys and values send information to the queries. So if we want to decode Spanish to English, we want the Spanish sequence to send information to the English sequence. So intuitively, you would want your queries to come from your English sequence and keys and values to come from your Spanish sequence. And in the language of conditioning, you would want your keys and values to condition your queries. So information you're taking from something and putting it into another sequence. So that's what we're going to be doing. And that is why we define it in this way. So we're sending information via the keys and the values from the Spanish sequence to the English sequence, such that we can decode the English sequence word by word to translate the Spanish sequence. So keys and values condition the queries. This works with other modalities as well. So this is what we see. You can see, remember, the outputs are dependent on the output sequence dimension is dependent on the queries, and the keys and the values are just going to make up those linear combinations that we have. That is why, again, we have our keys and our values from our Spanish sequence and our queries and outputs from our English sequence. Again, queries receive information, keys and values send information. So intuitively, it makes a lot of sense to have keys and values be our Spanish sequence and our queries be our English sequence, because we're translating from Spanish to English, where we want the Spanish sequence to send information to the English sequence. If we had it flipped, we would flip. So if we wanted to have English translate to Spanish, we would have English sequence be keys and values, and our Spanish sequence be our queries and outputs. So cross attention. Again, I have this arrow here saying keys send information to our queries. So notice how this is structured. This is not before. What we had is we had this 6x6 matrix. This is not. This is a n by m 6x7 matrix. And what this represents is this one here. So this one represents the word the. The word the is going to be an inner product with every Spanish token. So every token from the conditioning sequence. So every row represents a token from our sequence. It's going to be the weight, or it's going to be the inner product of this token with all the other tokens. And this is going to represent the weight for all of these tokens here. Remember, these are the weights that we're going to multiply by the values. And remember, the values come from our conditioning sequence. So that is what we have here. And you do that for all the tokens. This is what this represents. This represents a routing of information from our input sequence to our output, from our conditioning sequence to our sequence that we're modeling. So let's just look at SAT. So we take this part here, SAT. So here's SAT. Basically what this represents is how every Spanish word is going to be combined together to create this new representation of SAT. Notice how all SAT is doing is it is being multiplied by SAT isn't going to be combined in any way. All SAT is doing is it's kind of probing the Spanish words to know what information it wants to receive. So the word SAT here is our query, and every Spanish word are our keys, the conditioning sequence. All this is doing is this is basically saying how much of every word do I want. So SAT is saying, well, maybe I want a lot of this word and I don't want so much of this word because this word's useless for modeling translation. So that's what this is representing. This is representing how much of the conditioning sequence information do I want for this word here. So what we're going to do is I'm just going to define this linear combination, like SAT. Maybe it needs information from kind of its surroundings here. It doesn't need information from later parts of the sequence, like translation for mat. It doesn't need that. It doesn't need translation for cat. It doesn't need that information. This information is only needed to translate. So the information it needs to translate can just come from these tokens here. So 0.1, 0.1, 0.8. Maybe it needs a lot of information. It's just this is kind of an arbitrary combination, but all it's doing is it's taking a linear combination of all the conditioning words. So this becomes a combination of the conditioning sequence. And remember, if I am giving you a translation task, you know the entire input sequence. We don't need to mask anything. This is a bidirectional task. All these words, we already know what all these words are. We need it to be causal with respect to the sequence we're decoding, but we don't need it to be causal with respect to the conditioning sequence. So this token here, SAT, can be a combination of every word here. So that is this. That's this representing all the weights here for our conditioning sequence. Again, we don't need a causal mask because we know all our words. If I give you a sequence to translate, you know all the words in the sequence in the initial sequence. Do we need a padding mask? You do need a padding mask. If you mask along the columns, so you do need a padding mask, and that is because if we have, and the padding mask is with respect to the conditioning sequence. So if I am the word SAT and I am looking for information from the conditioning sequence, I am going to look at all these words. And notice how the word pad is in there. I don't want any information from the word pad, so I mask it along the columns. Again, if we go here, imagine this is our pad token. We would mask along the columns so that none of the words receive information from that pad token. So that's what you see here. And yeah, basically all cross attention is doing is it is saying, instead of formulating this attention matrix as a between my sequence, between just the sequence that I have, I'm going to be modeling it, or I'm going to have the queries be the input sequence and the keys and values from the conditioning sequence. So that's all this is saying, and this here is that representation. Hopefully that makes sense. So yeah, cross attention. Literally all it's doing is it's saying the conditioning sequence is sending information to every word in the sequence we're trying to model. So if I go back here, that is what you see here. This is query. I think this is key, and I think this is value. I think they have it flipped. So the keys and the values come from the conditioning sequence, and the query comes from the sequence you're decoding. So cross attention. Again, it doesn't need to be causal because causality, one, doesn't make any sense. It's not a square matrix, and two, you don't need it because you're taking information from the sequence where you know the entire sequence. Yeah, so hopefully that makes sense. So summary of attention names. Multi-head attention. Any type of attention with multiple heads. It can be anything. If it has multiple heads, multi-head. Bidirectional attention. Attention without a causal mask. Masked and causal attention. Attention with a causal mask. Self-attention is attention where Q, K, and V come from the input sequence. Cross-attention is where Q comes from the input sequence and K and V come from conditioning sequences. And any of these attentions can have a padding mask. So these are the attention names you'll probably see other places. So yeah, that is the basis for a lot of attention. So hopefully that is useful. Go look at the slides again. Hopefully they can be kind of helpful. But now we're going to get into more interesting things, linear attention. From now on, I'm going to be assuming unmasked, bidirectional, and self-attention. But if you really wanted to, you can swap out, say, the keys and the values to be cross-attention, or you can mask it to be causal or some other thing that you want it to be. And that also implies bidirectional. And I won't worry about padding tokens because that's annoying. It's even annoying to code up. So yeah, I'm not going to worry about that. Linear attention. So this is something I think is interesting. Something I'm doing research on right now, kind of. So problem with attention. So if you look at attention, you will notice there is a big problem. So let's just look at this. Softmax QK transpose V. This requires you to compute this matrix explicitly. You kind of. You basically have to do QK transpose, and then softmax, and then V. There is not really a way to get around that. So this is inefficient because you basically have to compute this big matrix. And remember, n is our sequence length. Now, Google claims they have 1 million tokens for their model. That means like you have to store this million by million matrix, which is, I mean, obviously they're not storing that because that I don't think any computer could store that. But this gets big quick, and this is a problem for softmax attention. And there is no way of getting around that because you have e to the kt. Now, this is e to the inner product of kt. I want you to try to decompose that. Good luck, because you can't. So this is a problem, and this is the reason why you have to explicitly compute softmax. Well, I say you can't. You can, just not in a practical way. It's just not worth it. It's useless. So you have to explicitly do QK and then softmax then V. So I say kind of because you can actually use flash attention. So if you are doing attention, you should be using flash attention. You should not be using, well, maybe there's another method that's faster. Not that I know of. So I don't know, use flash attention. It should not be normal attention. You can see it's way faster, and it's also way more efficient in terms, it's way more efficient in terms of memory and time. Literally no reason not to do it. One thing to note is that it is literally performing the exact same output. So the output is exactly the same. It just does it in memory in a very, very efficient way. This is not a CUDA kernel lecture, so I'm not going to be talking about how this happens. There are plenty of those online talking about how flash attention works, but it does it in an efficient way. Use flash attention. Another thing to note is they actually transpose the head and sequence dimension, so if you use it, watch out for that. So yeah, it looks like it was cut off a little bit here, but let's translate this to an alternate form. So this is our attention equation. What we're going to do is let's try to find a way. Let's hypothetically find a way to make this more efficient. So what we can do is we're going to translate this to a different form. And the second form is, well, let's just define softmax as big F. And let's define the exponentials as little f. You'll see where this goes in a second. So all we're doing is we're redefining exponentials as little f, and we're redefining softmax as big F. Now, imagine we have little f here. Now, let's use a different function other than the exponential. Don't worry about how expressive it is. Just go with me for now. Let's use a different function on f. Now, let's say we use a function that can be decomposed. So we have f of qt and ks transpose. Imagine if f can be decomposed into two functions, one on q and one on k. So f is now a function. F is equal to phi of q and psi of k. So I'm going to define these as tildes because it is much easier to write. But basically, we have f of qk transpose, and we're going to redefine this as a function. Instead of the exponential, we're going to redefine it as a function on q and a function on k. And this becomes q tota and k tota, where q tota is the function on q, and k tota is the function on k. So that's what you see here. So what does this give us? Is this good? Yes, it is. So yeah, again, alternate form. This comes from I think this is the original linear attention paper. I think my head is blocking it. It's there in the slides. What slide is this? 83. It's there in the slides. So they use elu plus 1 as their function. And yeah, so f here, this is our f. F of qk transpose, we're going to take phi of q, psi of k. So f can be decomposed. This is using a kernel function. So if we define f as a kernel function, we can decompose it. Specifically, a kernel function that can be decomposed into two functions. So this is a function on q, and a function on the vector q, and a function on the vector k. Now I'm going to define them to be equal, and I'm going to define them to both be elu plus 1, as they do in this paper, but you can use relu if you wanted to. And specifically, what you want is you want a non-zero, a function that produces non-zero values, and that is because of this denominator here. If it are non-negative values, and you want the sum to be non-zero because of this here. Like if I produce negative values, you run into problems. Don't do that. Well, if you do, you're going to have to worry about things. You can. There are formulations where you can. It just becomes problematic. Just for now, I'm going to say they must be non-negative. But if you make it negative, this runs into problems. For example, if I divide by this very large value, or if I divide by this very large, or if I divide by positives and negatives in the summation, you run into like exploding values, so exploding magnitudes. It's a mess. So I'm saying they're all positive here, all non-zero, and that's what you get with elu plus 1. It's basically, it looks like relu, just more curvy, or you could use relu. So one of those two. So basically what we're doing is we're taking this kernel function, we're defining a kernel function that can be decomposed into a function on the vector q and a function on the vector k, and I'm defining that as elu plus 1, as in this paper, and I'm defining that as q tota and k tota for notational purposes to make it way easier for me to look at. So I'm also going to be removing the denominator because it's still linear, or it still works with the denominator. It's just, it gets in the way. It removes from the abstraction I'm trying to build and the intuition I'm trying to build. So removing the denominator, but it does work with the denominator if you add it back. You also don't need the denominator. Side note, just I'm removing it. It gets in the way. So here, this is what we have. This is going to be the equation I'm working with. Remember, q tilde t is the elu plus 1 of qt, and k tilde s transpose is the elu plus 1 of k s transpose. So here, what we can do is, this is our formula, and this is just qkv here. And what this allows you to do is either do a multiplication on the left, or do a multiplication on the right. So as you can see here, in normal attention, what you would have is you would have softmax of qk transpose. So you have to do a multiplication of q and k first, which gives you this n squared by d, or this n squared matrix. And then you multiply it by the values. And this forces you to have this really, really large matrix. However, with linear attention, which is what this is called, you can change the order of operations and instead do k transpose v. You couldn't do that with the exponential before, or you couldn't do that because we had the exponential before. So if you do k transpose v, then you have something on the order of d, which is usually much smaller than n. For example, n could be 1,000,000, while n varies 1 and 2, n could be really, really large. It basically restricts you from producing more tokens. D is always static, and D is actually not D, it is the head dimension. So, for example, in llama or some of the models like use a dimension of like 4000 or 4096 or 1024, a large dimension. But this is the head dimension, so this can be something like 32 or 64. And 32 or 64 squared is much, much smaller than any sequence dimension you have. So this is much nicer to compute. And it's the same output because it's just changing order of operations. And yeah, it's under matrix multiplication rules. This is fine. You get the same output. So yeah, linear attention. That's basically the idea. So all you do is you swap the left multiplication with the right multiplication. Well, first you change the function. You change it from e to, say, elu plus 1. And now that it's a function on q and a function on k, you can then do a right multiplication instead of a left multiplication first. Or you do k transpose v instead of q k transpose first. Now, we can make this causal. So like this is fine. This is easy to compute. You can do this. It's not hard. Easy to compute. You code it up. You code this up real quick. Now, if you add a causal mask, so this is easy if you're modeling bidirectional stuff, but if you're modeling causal things like normal text, next token prediction, you have to add a mask, and this mask makes everything annoying. So if you add a mask, as I mentioned before, you can use a binary mask. So instead of having zeros, first off, instead of doing a additive mask, you do a multiplicative mask. So instead of having zeros here, you would have ones where you want attention to go, and you have zeros where you don't want attention to go. So what you do is you multiply your qk transpose with this mask. So instead of adding it, you multiply it. So instead of negative infinity representing do not send information, 0 does, and instead of 0 representing send information, 1 does. So it's multiplicative instead of additive. So yeah, you multiply that on the attention matrix here. And the reason you use this is because you don't have the exponential of the inner product. If you have the exponential of the inner product, you have to use negative infinity, or you do weird things with the denominator and stuff. You use negative infinity, but if you have something like this, you just multiply it by the mask here. Yeah. So multiplicative mask, that's what we're using here. So this is annoying. This is, like, it may seem like a dead end because, like, here, what I said is you can do qk transpose, and you can swap that over the order of operations, and you k transpose v. So here you can't do that. You have to explicitly compute this. The reason you can't do that is because you can't decompose this mask into a vector on n. Like, you have to have an n by n mask. If this was a padding mask, it's fine. You just need to multiply the padding mask by the keys, and it's a vector instead. That's fine. You can decompose the padding mask into 2 vectors. You cannot decompose this mask into 2 vectors. Try hard, it won't work. So you can't decompose this mask, which means you have to specifically do the qk transpose inner product and then multiply by m. And that sucks because we basically got nowhere, and we have to deal with softmax, and you might as well just use softmax attention at this point. Except there is hope. Is this a dead end? No, it's not. It's not a dead end, or else nobody would use it. So, if it was a dead end, yeah, it would literally be useless. So this is just another way of representing it. Basically, this is representing the output at time t, and I'm going to break this down step by step. So I'm representing it like this. This is just representing one of the rows here. So the output at time t is equal to the sum from 1 to n of all of the inner product of our query at time t multiplied by the key at time t multiplied by m at time ts multiplied by the values. So this represents our attention value, this masks said attention value, and this is our value. So n or s iterates from along the row here. So this is the row, the query along the row, and we're iterating along the row here for the summation. So for example, if we were iterating along this row, our mask would be 1, 1, and then 0, 0, 0. So that's what you would see here. You would see an attention value, and then you would see 0, 0, 0 because of the mask. So yeah, this is just iterating along the row. Now, what we can do is, so we have this mask here. What we can do is, like if we iterate along this row, you'll see that attention only exists up to the diagonal, which means we can iterate up to token t. So instead of having this mask here, we'll just remove the mask and iterate up to token t instead of token n, because anything past token t is going to be 0 anyways. So we change the summation and we remove the mask such that s iterates from 1 to t instead of s iterating from to the end of the sequence, where the end of the sequence is just removed. So yeah, that's just iterating. Instead of iterating 1, 1, 0, 0, 0, you just iterate up to this token here. So that is this. Yes, just iterate up to token t. Now, the nice thing is we can just move q outside, because q does not depend on the indices of the summation at all. So we'll move q outside. So move it outside. Cool. Now, this is a nice representation because all this is a recurrent neural network. So you can see here, this summation here is going to be our hidden state that we're summing up, and this here will be our output projection. So here, here you see our hidden state here is going to be equal to the summation of the outer product of all of our keys and our values. Remember, this is our outer product here, outer product representation. So what we're going to do is we're going to take the outer product and we're going to add that every time we have a new token. So every time we have a new token, we take the outer product of our keys and our values, we add it to the hidden state, and for every token, we can get to the output representation of that token by observing the hidden state with our queries. So that's just what we have here. It's just, now you have a recurrent form for that. So this is our recurrent form, hidden state at time t-1 plus our the outer product of the keys and values. Yes, this is our recurrent neural network. So queries are output projection, keys and values are hidden state, essentially. So you have this d by d hidden state, and our queries are going to be an output projection for that. So here, you can see ht is a hidden state. This is a summation over the time steps up to time t, and that can be represented as this recurrence formulation, where you have h at time t-1 plus our current, plus this inner product here of k transpose v. And this here should be a 1. That should not be a n. And this here should be a t. So what you're doing is you're taking the inner product, or you're taking the outer product of our keys and our values, where you're just summing them along all, that should be a 1. These should be a 1 here. So 1, 1, you're taking the outer product of our keys and our values, and you're summing all of those outer products together until you reach time step t, where you do this output projection here. That's all this is saying. So recurrent neural network, the simplest recurrent neural network you could have. It's just additive. And the nice part about this is a recurrent neural network across time is constant in space, where the space complexity, or the memory complexity, is equal to d squared. It's equal to the hidden state size. And you update this n times, so you update it however many tokens you have in the sequence. So recurrent neural network formulation. So yeah, there's basically two modes you have here. You have a recurrent mode and a parallel mode. So in parallel mode, you have a really, really fast computation. This is one matrix multiplication, or this is, you basically have this matrix multiplication that you compute. It's fast. So, the parallel mode is actually over here. This is parallel mode right here. Basically, you do the inner product, you multiply it by the mask, and then you multiply by the values. So parallel mode, really fast, one matrix multiplication, one Hadamard product, and then another matrix multiplication. So really, really fast in terms of compute speed. The second option, however, this takes up n squared memory, so really bad in terms of memory. The second option is you have this recurrent mode. So this recurrent mode is constant in terms of memory, it's d squared. However, it takes a really long time to compute because you have this iterative task which GPUs suck at. So you have two modes you can do. You can do a parallel mode, or you can do a recurrent mode. One is really, really fast, but sucks in terms of memory. One is really, really slow, but is amazing in memory. And what you do is you do something in the middle. I'm not going to get into that here, but what you do is something in the middle where you do a semi-parallel and semi-recurrent model. But this is something you don't get with softmax attention. So where did this deviate from softmax attention? it deviated when we removed the exponential. So removing the you can see here in this formulation, we can move the query outside, and that allows us to define a hidden state because this is only indexed by us. However, here, you can't move the query outside because you can't decompose the exponential of qtks transpose. So you can't move qt outside, which means you can't formulate a recurrent mode for this. So that means linear attention is nice because even with the mask, with the mask it's a recurrent neural network, while without the mask it's not. But with the mask, you have a form that is linear in terms of memory still. Even though you have this mask in the way and you have to do an annoying CUDA kernel, it still is linear in terms of memory, while softmax attention must be quadratic. There's no getting around that. There is no recurrent representation. It is quadratic. So this is the RNN diagram. So this is our hidden state here. Hidden state, you take the outer product of k and v. So these are all the past keys and values. This is our current token. So maybe this is the cat sat. This represents the cat sat, the sum of all three of those outer products. And this represents the key query and value for the word on. So you have your keys, you have your values, you take the outer product of those two. This gives you a new matrix, which you then add to your hidden state. So you update your hidden state as shown here. And then you do an output projection. So Q, outer inner product on the left of the hidden state, and you get your output. Literally like the most simple recurrent neural network you could possibly form, but that's linear attention. There you go. So drawback, it's not as terms of good of accuracy. So I stole this online. Forget about the blue part. I just wanted this graph. So you can see here, orange is linear attention, green is softmax attention. This is, I don't know what, imagine this is accurate, or this is perplexity. So it is like, it's worse. It's worse. And that's expected because it's basically a linear approximation of softmax attention. So yeah, it's a drawback. You have softmax attention, very inefficient to compute, very, very expressive. Linear attention, on the other hand, is not efficient to compute, or it is very efficient to compute, but not as expressive as softmax attention. So you have this trade-off. And what you're seeing is we saw a lot of these linear models be developed in the past 5-ish years. And what you're seeing now are, I think it was 5 years, are these hybrid models where you have some softmax attention and some linear attention, but you can get a lot. Like if you have only a few softmax attention blocks, you still get this full attention routing, this full attention expressiveness. But if you have a few linear attention, or if you have a lot of linear attention around those softmax attention, you get a very, very efficient model that is very expressive as well. And sometimes you see linear attention be a little more, like linear attention and softmax attention together be better than normal softmax attention, which is very weird, and nobody knows why. So this is an active area of research, and it is very cool to see it to see how it's been developing. So list of linear attention. The original linear attention has a lot of formulations based off of it. I have one that I put here. The reason I put it here is because I don't know, shameless plug, I guess. I don't. It's there. But basically, it's slightly different from linear attention in that the denominator is not the sum. It's slightly different. Mamba 2. Mamba 2 is insanely good. It is the best linear attention out there. If you're going to use linear attention, use that. RWKV is... That's a mess. That is... I guess you could try to read it, but that's a mess to read. Mamba 2 is a very smart design for how to produce linear attention. RWKV is a very... that is an engineering design if I've ever seen one. You look at Mamba 2, you're like, that is very nice. You look at RWKV and you're like, what the heck am I looking at, man? This is going to be hard to read. Mamba 2, highly recommend that paper. RWKV, I haven't really tried it. Apparently it's insanely good. To me, it seems like it's way over-engineered. LSTM, yeah. So basically, this is an RNN. Why not call an LSTM linear attention at this point? If we're calling linear attention, but linear attention is an RNN, then why is an RNN linear attention? So LSTM, there you go. LSTM is a type of linear attention because it's an RNN. Anyways, it's more of a joke, but yeah, there's a lot of linear attention methods out there. I would suggest reading Mamba 2 to or look at something with Mamba 2 because that one is the paper's good. There's a lot of good theory in there. They have a lot of really cool things that they do with it. And it is also really, really good. I am surprised at why it works how good it is. The curve is much lower. It's not as good as softmax extension, but it's really good. Gradient-based RNN slash linear attention. So there's this new kind of linear attention type kind of forming, and I'll show you it is linear attention. And you're going to have to bear with me through this explanation. It's going to seem unintuitive at first, but we'll get there. Basically, the idea is we're going to be defining. So let me go back here. We update our hidden state based off the sum. So what we're going to be doing is we're going to be defining the update rule to our hidden state based off the gradient to a loss function. And this loss function is going to be a loss function on this hidden state. So there's this idea of like meta learning and stuff like that. Oh, we have a model inside the model that's learning a task that the outside model is giving to that model. I find that confusing. So instead, we'll see, it leads to a very similar formulation. And it becomes obvious once we get to the end formulation. Just bear with me as I go through this explanation. So let us define a loss function. So again, what we're going to have is we're going to have this meta learner, this model, where this model is defined by WT. So it doesn't have to be a weight matrix. It could be an MLP if you want it to be. For all practical purposes, it is a weight matrix. If you don't use a weight matrix, it's impractical to compute. You basically have an RNN, and you might as well not do this at this point. So it's not efficient. So WT is a weight matrix. WT is going to be optimized by this loss function here. So just imagine you have a normal neural network. For a normal neural network, you give it a loss function, and you optimize it using gradient descent. We're going to be doing that here, except WT is going to be our model, L is going to be our loss function, and instead of this being our loss function for our model, we're going to have this as a model inside another model. So we have our normal model, normal transformer, learning next token prediction. And for our normal transformer model, we have attention. But instead of attention, we're going to replace this with this model, this meta learner, that is going to update its hidden state every time it sees a token based off this loss function. So what is this loss function? This loss function is basically this reconstruction. So we'll see where this leads, but we're defining this reconstruction loss here, and the model is going to learn based off this. So yeah, reconstruction loss. Let's see how this becomes an RNN. So we have this reconstruction loss. Our inside model is going to learn based off that, and it's going to learn by gradient descent. So what we do is we define this gradient with respect to the weight matrix itself. So we take the gradient of the loss with respect to the weight matrix, and this gives us this formula here. So this is our loss. This is just the gradient of that, and you can see this is d by d, which looks a little like the d by d hidden state we saw earlier. Which I'm just going to lead to that. So this is our gradient. This is it. So if you want to derive it, you'll get this. Note, our weight matrix is d by d. Our input token is x at time t, which is just a vector. This is a vector. This is a vector. This is the outer product here, xt transpose. Updating the weight matrix. So this is what I derived before. You have your loss. You have your gradient here. What we're going to do is we're going to define a gradient descent step. So what is a gradient descent step? Well, it is w at time t. So we're updating w at time t minus learning rate times gradient. I think they use I forget what they used. I think it was nu as their Greek letter. I'm using beta because the compiler I had didn't have nu. So beta right here. So what is this equal to? So let's just throw the gradient here. You get this function here. Now if we move xt inside, you get this function here. So I'm just moving that inside the parentheses. And if you move beta inside, you get this function here. Yeah, so basically our update to our update rule is going to be, well, our update rule to our weight matrix is going to be w at time t plus 1 is going to be equal to the current w at time t plus this thing minus this thing, which is just this here. Same thing, just it'll become important why we're doing this in a little bit. Basically, this is going to be our hidden state update, just hint, hint. So yeah, let's redefine this in summation form. And basically what we're trying to do now is we're trying to get this in an efficient form. We just get trapped, and then I'm going to rederive things, and then we don't get trapped, and then we get the actual update rule we use. So this gives you, so this is our formulation that we had in the previous slide. Let's define this as a summation. So as a summation, we have w at time 0 minus all the gradients here. Times beta should be here. It's not, but it should be. Yeah. So that gives you this. Now there's a problem here, and the problem is w at time t is here, and ws is here, and that's really annoying because if ws is in your summation, then you can't really do things computationally efficient because that requires you to basically iterate over your entire sequence, and that is really annoying. And it makes a lot of sense that you would have to iterate over your entire sequence because this is gradient descent. You take a step with respect to where you are on the lost landscape, not W0. But what we're going to do is we're just going to say, well, what if we just replace WT with W0 instead? So yeah, that's what we're going to do. In practice, they actually do something in the middle. So they basically they do something called batch gradient descent, which is what we all know and love. So this is akin to this would be mini batch, or this would be just gradient descent, stochastic gradient descent, where every step is based off is like you have a batch size of 1, so stochastic gradient descent. Now if we define W0, this would just be gradient descent, full batch gradient descent. So if we define this as W0, what they do is something in the middle where they actually say, well, we'll take a step using what I'm going to derive in a second, and basically that'll you'll do this incrementally. So instead of it incrementally with respect to each token, you do it incrementally with respect to a batch of tokens. So you'll see what this derives in a second. It derives a really nice formula, and that nice formula, I'll talk about it once we get there. So this is really annoying. You can't compute this efficiently. You have to do this sum because you have w at time s right here. And that means you have to update w before you can to compute this sum. So you have to compute this sum using a recurrent scan along t. Very annoying. So if we just swap out wt with w0 in our loss function here, you get a very nice formula. So I I just rederive everything. So literally just replace wt with w0, and you get this summation here. So w at time t is equal to w0. Again, there should be a beta right here, of the summation from s equal to 1 to t of the gradient, which is equal to w at time 0 plus this. Now, this is nice because w does not, we don't have w depending on the rest of the sum here, which means you can compute this using a recurrent neural network in parallel. So much more efficient, rather than if you had ws here, which forces you to compute it in recurrent form. So there exists a parallel representation, which means you can compute every s at the same time because w is not dependent on s. However, because w was dependent on s before, you had to compute it in recurrent form. So yeah, let us. One other thing I want to mention is, as I was mentioning before, there exists a middle ground which is the best. So what you do is you basically bring the sum not out to t, but you bring it out to some intermediate step, maybe say 16 or something like that. So you do the parallel operation up to size 16, and then you update W, and then you do that over and over again. So that's akin to mini batch gradient descent, but I won't get into that. I just want to show kind of the main idea behind this and how this relates to a recurrent neural network or linear attention. So this is our thing, this is our update rule. Now what if we define this as H instead of W? So I'm literally just translating this to, I'm just redefining W as H. That's what I'm doing here. Now, what if I factor out x at time s here? So, or x at time s times x at time s transpose. So if I factor this out, we'll get something interesting, and it's just linear attention. So this is our linear attention hidden state. This is our new hidden state. And all you do is you add h0. That's essentially all you're adding. You also add beta, but constant, probably not that big of a deal. You basically add h0. So basically, we did all this driving, and we get a hidden state. We get basically a starting point. So here you basically start with h0 equal to 0. Here you start with h0 not equal to 0. And that is essentially what we get from this. Now, there are things that make this more expressive. So I said this is akin to gradient descent. That means you can add momentum and stuff, and that makes it really, really inefficient and annoying to compute. Makes it a little bit better, but this is very new in terms of research. So yeah, this is the parallel between this new gradient formulation thing and linear attention. Now, this is the final equation for completeness. So I'm just taking this equation that we derived, throwing it here. Remember how in linear attention we had an output projection, we had this hidden state. Same idea, you have an output projection here on the hidden state at time t. So exact same thing, you just have a initial hidden state. And again, that initial hidden state will update as you, if you use the form they had in the paper, but I'm not going to go over that here. Just want to make the parallels. Yes, so my thoughts on this. I do think it's an interesting direction. Not so much, I think it's an interesting direction because it's a different way of looking at it, and there's a lot of theory. Like, we know how to optimize models pretty well. Sure, it's slow, it requires gradient descent, but if gradient descent under this formulation gives us linear attention, then and we know we know how to optimize gradient descent pretty well, then perhaps there are things we can take from gradient descent to throw in linear attention to make it optimize well. There's a lot of things you can add to linear attention, but this can help add things that are actually useful. Titans tried to do this, and Titans were apparently Transformers V2. That was annoying because they aren't. It's basically this, but with like a lot of bells and whistles, and it's this but with momentum. So, but they make it this. I don't know if it was them who made it a big thing, or if it was just the press and media. But Transformers V2, no, Titans is not Transformers V2. But anyways, besides the annoyance, there are things trying to make this actually like using this method, and this method is very, very new. It comes from a paper called like Learning to Learn at Test Time. So yeah, it's a very interesting direction, and I think it can lead to a lot of interesting results. It's very new. So RNNs versus transformer hidden state. So gone over our like linear attention and RNNs, gone over transformers. Now let's talk about how they both have a hidden state, just real quick. So recall linear attention formulas. Hidden state obviously is the hidden state plus the outer product of our keys and our values. Awesome. Hidden state is d squared. Easy as that. Transformers, on the other hand, are much more complicated, or like softmax attention. Much more complicated. Basically, you do have a hidden state, and this is called a KV cache. So if you heard a KV cache, this is where it comes from. Basically, your hidden state can be the So this has to be causal, by the way. So if it's not causal, you don't do this. It just doesn't make sense. If it's causal, you can form a KV cache. So remember, for a causal representation, we need all the keys and the values up to time t. So that means we cache all the keys and values up to time t. And to do that, you basically form this concatenation where you have this block where every time you see a new token, you add the key and value to that cache. And this cache grows linearly. So this cache is just the concatenation of all tokens. So here you can see this is our query at time t. Our keys are from 1 to t, and our values are from 1 to t. And that means every time you go to the next state, the next part of your sequence, you add a new token to your key cache and your value cache. So you just concatenate it, and then you have to compute this all over again. So this one, easy. You do the outer product, you add it to the hidden state. This one is not so easy. You have to concatenate every token to the cache. So this is how I'm representing it here. And that is because you can't move the queries outside the sum. So yeah, this is what you have. And you need to recompute softmax every time. While here, all you have to do is add and do this output projection. Here, you have to concat along k, concat along v, do softmax, and then you're good. So yeah, there exists a recurrent formulation. The RNN is just 2 RNNs where you do concatenation instead of addition, and the output projection is recomputing softmax along the row. So basically this is giving you your keys and values for the row in the softmax or in the attention matrix. So now to the weird and I guess not so interesting parts. Well, we're almost at the end of the presentation, but the weird parts. So I can formulate an MLP as attention, and there was this paper called Potention, or actually it's not Potention. I forget what it was called. They form a layer called Potention, and basically they don't mention that this is an MLP, but it basically is, and yeah, it basically is Potention, or it basically is an MLP. It isn't basically an MLP. It is an MLP. So I just find it funny that they basically derive an MLP from attention, and they put a bad nonlinearity on it. So they put softmax on it because, well, what nonlinearity does attention use? Well, it uses softmax, so they just throw softmax at it, and they call this Potention layer, and they don't mention it's an MLP, and it's an MLP with a bad activation function. There's also a layer called memory layers at scale, and I'm going to talk about that later. It's definitely a better paper, but it still is like, it's basically an MLP, just as an index on it. So let's just derive it. Yeah, MLP as attention. Basically, we're going to be talking about cross attention. So Q, K, V. Just what we know and love. Q, K, V. I'm going to define this as F to generalize it, but you can define this as softmax if you want. So 3 projections. First thing we're going to do is we're going to define V and K as learnable. So instead of this being so here this is a projection of a sequence. Here we're going to make them static and learnable. So before we had a sequence of size m by d, and we projected it to our keys and our values. Here, we're not going to have a sequence, and m is not going to represent a sequence dimension. It's going to represent a inner dimension. So imagine I have an MLP, and imagine I have an MLP that takes in a vector of size d. It projects it to a size of 4d. The m would be the 4d. And then imagine that projects it back down to d. E would be our d. So it would be d, 4d, and then d. So what we can do is we can merge W, Q, and K because they're both learnables, and just merge them together. You can merge 2 learnable matrices together, and it's just as expressive because there's no nonlinearity in between. So I'm just merging W, Q, and K. So yeah, combine them into the K projection. Now let me redefine K transpose here. I'm going to redefine that as W up, and I'm going to redefine V theta as W down. So I'm also going to redefine M as D inner, and I'm going to keep E the same, and I'm going to keep this as X. So magically, we get an MLP. Look at that. This is So, like, in transformers, how you have your attention and then you have MLP. This is an MLP. And all I did was do two things. I made our keys static, a static weight matrix, and I made our values a static weight matrix. Now, if I have this is called potential. And notice how I just redefined this as W up and W down. This is an MLP. They're the same thing. So yeah, MLP and attention, same. Like attention, you have dynamic keys and values, where keys and values are based off a sequence. And MLP, you can redefine it such that the keys and the values are static, not based off an input sequence. So that's this here. So there exists a formulation where we can translate it. So if you see this anywhere, it is just, it's not attention, it's an MLP. So if you make K and V not learnable, you get an MLP. Or if you make K and V static and not with respect to the input sequence, you get an MLP. If you have K and V learnable with respect to the input sequence, they are attention. So let's go one step further. Let's turn this into a Mo. So I just like, I'm just kind of having fun with this. Now, it's kind of described in memory layers at scale. So memory layers at scale basically take this and they define an index on it, an index on W up and W down, and basically a Mo. So I'll show that. What I'm deriving is not what they define in memory layers. They have an index outside. The index is just slightly in a different location, but it's basically the same idea. So yeah, hopefully the MLP makes sense. This here, I'll define as the MLP and then define as an index on it. So here we start again with softmax attention, good old softmax attention. Here, I'm keeping softmax this time. I'm going to rename the matrix to WR, so I'm renaming KT to WR. I'm making K static, and I'm making V, I'm renaming V to E, and I'm making V static. So basically I'm taking what we had here, and I'm renaming this and this. So this here is the exact same thing we had before, except for the MLP definition, except softmax, I have softmax here as F. Instead of there being W up, I have WR. Instead of there being W down, I have E. So it's the same thing we have in MLP as attention that I showed before. Now what I'm going to do is I'm just going to define this part here as R. So R is equal to the softmax of this here, and this is essentially our router. You can think of this as again, this is an MLP, where this is our inner dimension, so our up projection, and this is our down projection for D. So you can think of this as M experts in a way, where every expert, this is like a dense Mo in a way, and this is just a sum of all the experts. So dense Mo because we're not indexing anything, where this is our router, where this becomes an N by M matrix, where this basically says, this gives a weight for every expert, and this just takes all the experts. Now it's not Mo unless you add an index on it, so what we're going to do is we're going to define an index, where the index is here. So first thing we do is we do this projection here, which is just this. So this is our router projection, and we're going to index it. So we take our router projection, and we take the top K indices along the rows, and if we treat M as the number of experts, we are basically indexing the experts for every token. So we have a token, the token is projected from D dimensions to M dimensions, where M represents the number of experts. We take the softmax over that. We then say, what are the top M weights? And we take the indices of that here. So this here is our index for the top K, for the indices of the top K weights in our router, which basically says I have M experts. These are the top K to send to accumulate. Then what we're going to do is we're going to index our expert set. So remember, our expert set is M by D, and our router weights, because for mixture of experts to make this differentiable, you need to multiply by the weights. So you index both these and you get this. So instead of this being n by m, this is n by k. And instead of this being m by d, this is k by d. So one way to look at this, you have a token. The token says, I have m experts. I'm going to choose k of them. You have it project to all m experts, and you say, I only want the top k of those. So you take those weights and you only multiply that by the top k experts. So basically, you define these weights and you do a linear combination of all those experts. Remember, in our original attention formulation, this was a weight matrix, this was our matrix of values, and this defines a linear combination. So all you're doing is you're defining a linear combination of the experts for every token. So that's what this is doing here. Another way to look at this is it's just an MLP where you take a subset of the dimensions. So 3 ways to look at it. A MO with k selected experts from a pool of m, where each expert is just a vector. So that's one way to look at it. You can look at it as a MOE, where every expert is the simplest thing you could think of. It's just a vector. Second way to look at it is an MLP with a softmax activation function, and instead of saying I'm going to do an up projection to say 4D, if I'm just selecting k, where k is equal to say 2D, then I will project to 4D my inner dimension, but I'm taking a subset of that inner dimension as opposed to projecting to the full inner dimension. So in a way, you can think of this as dropout. Yeah, you could think of this dropout. So that's one way to look at it. An MLP would drop out, and activation function is softmax. A third way is attention, where the keys and the values are static and learnable, and we subset the number of keys and values we use. So that's another way of looking at it. So if this is our attention matrix here, this defines a linear combination of the experts for every token. So another way to look at it. This is just here because there exist papers out there which do this. So yeah, I mean, is it a good idea? Probably not. It's basically an MLP with dropout, but it exists. And for the sake of it, let me just do this where we make it learnable. So you can actually redefine. You can make it again as a attention. So instead of this being the softmax of x and WR, where WR is static, you can say, well, what if we have Q and K, and then what if we have V here? So we're going to go all the way back to normal attention. We're going to have these as QKV projections, and we're going to do Mo on there. So you can do that. It exists. It is right here, and it does things. Is it good? Probably not. Just use an MLP. But in case it exists somewhere, there you go. Basically, what this is attention, but it's sparse attention. So you're only selecting the top k weights for every token. So basically, I'm saying, while I could do a linear combination of all the values, I'm only going to do a linear combination of the top k values that I select. So there we go. That was a long presentation, but that is a lot of stuff on attention. Hopefully this was useful. Let me know if you have any questions. But yeah, there we go.